So in this video, our essential question today, make sure you copy it down, is how can we interpret and compare graphs? So we're going to kind of be combining what we've been working with analyzing graphs and also with our function notation. So what I want you to do now is just pause, try the warm-up on your own. All right, so this warm-up shows the populations of both Baltimore and Cleveland throughout the 20th century. B of T is the population of Baltimore, so that's our solid blue there, and C of T is the population of Cleveland. That is represented by the red dashed. So first question is asking us to just estimate B of 1930. All right, so that's my input, that's my time. Time is 1930. So I go over here to 1930 for Baltimore. All right, so B of 1930 is equal to 800,000. So what does that mean in this situation? In 1930, the population of Baltimore was 800,000. That's what that sentence is saying in math, okay? Number two, here are pairs of statements about the two populations. In each pair, which statement is true? Okay, so in 2A, you're comparing the population during the year 2000. All right, this first one is saying, is Baltimore's population in 2000 bigger than Cleveland's? Or in the second statement, is Baltimore's population less than Cleveland's in 2000? So we go over and we look at 2000. We see that the populations of 2000 are these two pink points here. Which one of those is lower than the other? Cleveland is lower, okay? So that means that the population of Baltimore in 2000 was greater than the population of Cleveland in 2000, all right? And then 2B is comparing at 1900. Were the populations, this one's saying were the populations equal, or was Baltimore more than Cleveland? So let's look at 1900. We can see here that they're clearly not the same. Baltimore is a higher population than Cleveland, so the second statement would be the one that is true. All right, now the last statement does ask if the populations were ever the same. So we are going to be looking for the intersection points there. We're going to see if the two functions meet. So we see an intersection right around here, and we see an intersection up here. And then that's the last time that those two populations were the same. Oops, sorry, I erased that point. Let me try to bring that back. There we go. All right, so were the two populations ever the same? If so, when? So right around, this point might have been a little big, right around 1910 here, in 1910, and in maybe about 1942 about. It's a little bit after 1940. So that's how we could say when those populations were the same. If we wanted to write it in function notation, we could say Baltimore's population in 1910 was equal to Cleveland's population in 1910. We could also say that Baltimore's population in 1942 was equal to Cleveland's population in 1942. So that's how we would write that in function notation to show that the two populations were the same. Okay, so that's the warm-up. Check to see how you did on those, and then we'll move on to example 1. In example 1, dealing with a different function here, H of T is the percentage of homes in the United States that have a landline phone, blast from the past, landline phone. C of T is the percentage of homes with only a cell phone, so no landline, just a cell phone. So here are the graphs of those two functions. This solid blue, again, that's our landline, that's H of T, and our dotted red, that's our C of T, that's our cell phones. All right, so the first one is asking us to estimate both H of 2006 and C of 2006, and then explain what those are telling us. So H of 2006, if I go over here, H is talking about landlines, which is our solid blue. So I'm going to go up there. That's about, we'll say 83. And so when we put that together in a sentence, we're saying in 2006, what happened? 83% of homes had a landline. okay? So that's what is happening in 2006 for landlines. Now let's look at the cell phones in 2006. So in 2006, that's going to be, if 83% had a landline, then about 17%, the remaining, is going to just have cell phones. So in 2006, 17% of homes had just a cell phone. So we found those two estimates based off the graph. Now, number 2 is saying, what's the approximate solution? So the solution here is meaning we need to solve for t. All right, so we want to solve for t when c of t equals 20. So this is the output here. We're getting an output of 20%. And so we want to figure out in what year did 20% of homes own a cell phone. All right, so if we bring this over here, we see that we're getting out 20% right around 2008. So t is going to equal 2008. Explain what the solution means. That means in 2008, 20% of homes had just a cell phone. Okay, so that is what that solution means. When we actually work backwards to find the input, we find that the input is 2008. Okay, so that is the first two problems. Now we're still in the landline cell phone world, just on the second page. We're going to determine if each equation is true. So C of 2011 equals H of 2011. So that's saying in 2011, the percents between cell phones and just landlines were the same. So if I go over here to 2011, clearly these are not the same. Clearly those are not the same. So instead, it looks like cell phones is still less than landline phones in 2011. Okay, so that's how we could modify that. We were going to make that less than here. Okay, now what about in 2015? Were the two percentages equal? Well, let's look over here in 2015 right here. Do you see that that's where they intersect? Yes, true. It's where the functions intersect. Okay, so that one is true. This first one, we didn't write it there, but we can put that that's false there. Okay, so we want to, in number 4, we want to determine 2 years where C of t is less than H of t. So think about what that's saying. That's saying that the cell phone percent is less than the landline percent. Well, if we look over here on the graph, that's happening every time the cell phone is less than the landline. Okay, so up to that intersection point, and then after that is where cell phones kind of take over from the landlines, but we want the cell phones to be less than the landlines. All right, so as long as you pick any year between 2004 up to 2015. Okay, up to, but I'm going to say, but not including 2015. So like if you wanted just 2 years, just pick 2 years that are in that interval. Like we could say 2008 and 2012, for example. So those would be 2 years where cell phones percent is less than landline percent. Okay? So the last question for this, between these 2 years, did the percentage of homes with landlines decrease at the same rate at which the percentage of cell phone homes only increased? Okay, so it's a little bit confusing of a question, but really all this is asking us to do is find the average rate of change. Okay, you see it's using that word rate in the question, in the sentence, or in the question. So that's telling you, kind of giving you a hint of what you're trying to do. All right, so if we look at if we look at landlines, H of T, okay? H of T, like it started up here at, I don't know, we'll say about 90%. And then it went down all the way to, what year are we looking at? To 2015, to about 50%. Okay? And that happened in 2004 to 2015. So if we subtract those, we went down about 40% over the span of, so we went down 40% over the span of 11 years. So I go to my calculator, I just take negative 40 divided by 11, and that's about negative 3.64% per year. So landlines are going down about 3.64% every year. All right, let's compare that to the cell phones. Okay, for the cell phones here, we started at about like 5%, maybe, kind of just estimating off of here, started at about 5% and then went up to 50. So 5 minus 50, and then that was 2004 minus 2015. So if we check this out, we have a negative over a negative because it's increasing, so it's got to be positive here. That's going to be about 4.09%. Okay, so 4.09% per year. So are they decreasing at the same rate? A very close rate, right? They're only off by like 0.5. So the rates are very close. The rate of change are very close there. Okay, which makes sense because as landline homes become more cell phone homes, that's going to decrease and also cause cell phones to increase. All right, so it makes sense that landline phones are decreasing at the same rate as cell phone homes increasing. Okay, so good on that example. So that's kind of our main example we're looking at today to kind of compare landlines to cell phones, and then also just kind of throw back to average rate of change and function notation. Okay, so if you have any questions there, please let me know. And if no, we'll move on to our last example. Okay, so example 3 is just giving us two functions, f and g, graphed on the same coordinate plane. All right, we're just going to answer these 3 questions. Decide which function value is greater for each given input. All right, so I just want you to pause the video here, try it on your own. Which function value is greater for the input? All right, so the first one says f of 2 or g of 2. So that's saying we're plugging in 2 for x, and we see that f is less than g there. So which function value is bigger? G is bigger. Okay. So next up, x is 4. So if we look at where x is 4 and we kind of compare, notice that they're equal. Notice that those are the same outputs. Both of them are 7. So those are equal. None of them are greater than the other. All right, next one is 6. We're plugging in 6 for x, and we look at the two outputs. Their f of 6 is bigger or is greater than g of 6 because f of 6 is getting a higher output than g. And then the last one here says f of 8 or g of 8, so we're plugging in 8 here. And notice that f of 8 is still higher. We're getting out a bigger output than g of 8, okay? Then the last one, number 2, is there any value at x at which the equation f of x equals g of x is true? Well, if they're equal, they need to be intersecting. So look for where they're intersecting. They're intersecting at 2 places here. Intersecting when x equals 4, and right here when x equals 9. So those are the 2 values of x at which these 2 functions are equal because they have the same exact output. All right. And then the last one, we want to identify at least two values where f of x is less than g of x. So f of x has to be under g of x. And there's two areas where this happens. Happens at the very beginning and it happens at the very end. Okay, so your answers may vary here because you just need to pick two value. Okay, so your answers may vary, but for some examples, we could pick x to be like 3 and x to be 11, something like that. When x is 3 and when x is 11, when I plug those in, f is giving me a smaller output than g is. Okay, so that's kind of just putting it all together. Please, if you have any questions, make sure to let me know. Other than that, thanks for watching.